Hello everyone. Today let's solve the problem number 110, balanced binary tree. So here you can just go through the question. They have just given a balanced tree, determine if it is height balance. So we are given a binary tree, and what we need to determine here, whether if it is height balanced or not. That's what we need to determine. So what is height balanced? Here they have clearly mentioned. If you hover on this, they have mentioned height balanced tree is a binary tree in which the depth of two subtrees of every node never differs by more than once. Never differs by more than once. That you need to keep in mind. So what they have given, here as a height balanced binary tree is defined as a tree in which the depth of the two subtrees. So here we have already solved the problem on finding the maximum depth of the binary tree, right? So we know what is depth. Here the depth of the two subtrees of every node should not differ by more than one. So that's what a height balanced tree is said to be. So a height balanced binary tree is defined as a tree in which the depth of two subtrees of every node never differs by more than one here. So that's what they have given here. Let's come to the example 1 here. Let's come to example 1 here. So here what they have given, example 1 here, it consists of 3, 9, 20, 3, 9, 20 and null because this doesn't consist of the subchildren, right? So they have given null, and finally 15 and 7. The output here they have given true. Why the output here is true? Because the left subtree here has a height of 1. You can clearly see this one. Left subtree is having a height of 1 here. We know this one, right? Left subtree is having a height of 1 and the right subtree is having height 2. You can just consider this one. Here it is having height of 2 here, right? So the left subtree has height of 1 and the right subtree has height of 2. So what is the absolute difference here? Absolute difference is nothing but 1 minus 2 here. This one minus this one, this height. 1 minus 2 will be 1. 1 and the result 1 is not greater than the 1. So the tree is said to be balanced here. So the output that we need to give here is true. I hope this is clear. Next, let's move on to the second example here. So second example, what they have given here, 1, 2, 1, 2, 2, here this one, 1, 2, 2, 3, 3, null, 4, 4 they have given here, 3, 3, this one, null, 4, 4. That's what they have given here. We don't have anything here, right? Null, 4, 4 they have given. So output is false here. Why the output is false here? The left subtree is having a height of 4. You can clearly see here, 1, 2, 3, 4. So let me consider this one, 1, 2, 3, 4 here. So the left subtree is having a height of 4. We know this one. And the right subtree is having a height of 1. We are having height of 1, right? So here this will be 1. Height of the subtree will be 1. And the absolute difference here is nothing but 4 minus 1, which is 3. And according to the height balance tree, it shouldn't be greater than 1, right? So obviously 3 is greater than 1 here. So the tree is not said to be balanced. So the output will be false here in this case. So yeah, this is it. Next, let's see the third example. So I'll just come here. Here root they have considered empty. So we don't have any element at all. We just have to return the output true, right? So this one also we need to consider edge case. This is one of the edge case one. We don't have empty tree. We have to return output true. This is important as well, right? So I hope the question is completely clear. Now let's see the approach. Then how can we solve this, and how can we articulate this one in the form of code, and then let's discuss the edge cases one by one, and finally then let's write the code and discuss the complexities of the code that we have written. Initially, as usual, let's discuss the approach. So the approach that we are going with here is we will be making use of DFS, post order traversal here. Just remember, we'll be making use of DFS with post order traversal, or DFS post order traversal. We'll be making use of as we know that, let's consider post order traversal. Post order traversal, just remember this one: left, right, and this one root will be deciding in this way for the post order traversal. So while we are solving the binary tree question, so we should be knowing about different trees, and we should be familiar with the this one, the recursion. We should be knowing the pre-order traversal, post-order traversal, as well as the level order traversal. Along with it, as I've said, we should be knowing about the recursion as well. So I hope this is clear. So at each node, what we'll do, the first step here, at each node, we will recursively find the height of left subtree. At each node, we'll be finding recursively, we'll recursively find the height of left subtree. And also the second thing is we will recursively find the height of right subtree as well. Left subtree and right subtree. Let me give here. So this is first step. After recursively finding the height of the left and right subtrees at each node, if the height difference between the left and right is greater than 1, if the height difference, we have already seen this one in the example, right? If the height difference between left and right is greater than 1, then we'll mark that one as not a balanced tree. So we know this one by the example. We have already considered this one in the example. We have already seen this one previously by considering the examples that they have given in the question. Finally, we will return the height of the current node as maximum, this one, max of left height comma right height plus 1 here. We will be I'll just keep here. This is simple. We will just return height of the current node, or let's consider current node itself. Current node as max of left height. I'll just give here LH plus comma right height plus 1 because the indexing of the binary tree starts from 0. Left height plus right height, left height comma right height plus 1. Max of left height and right height plus 1 because binary indexing starts from 1. So this will be the approach that we'll be going with. I hope this is completely clear. So next, let's discuss the edge cases one by one and then finally write the code. So the edge cases that we need to consider here is, first edge case, let's go with the empty tree. So when I say empty tree, let me give the input here, empty, root equals empty. Output will be true. We already saw this one in the example. So this is for empty tree. This is fine. This is first edge case. Let's move on with the second edge case, nothing but tree with only one node. So I'll just give here one element. Let's consider only one node or one element here. The output will be true here. For this, also the output will be true, right? So this is for the condition tree with only one node, right? So let's move on with the third edge case, nothing but here. In this case, perfectly balanced tree. When I say perfectly balanced tree, I'll just consider here root equals 1, 2, 3, 4, 5, 6, 7. This is fine. This is the input, perfectly balanced tree here. Here, then also the output will be true here. So I can just visualize in the same way that I had showed for the example 1, right? So I had showed clearly for the example 1 and example 2 that they have given in the question. So you can just visualize in the same way, or you can just try in the same way. The height, the absolute difference should not differ more than 1. It should not be greater than 1, right? So if it is greater than 1, then the tree is said to be not balanced, unbalanced, then the output has to be false. In this case, it doesn't differ as it is, as we are going with balanced tree, perfectly balanced tree, right? So the output will be quite obviously true here. Let's go with the final edge case, nothing but highly unbalanced tree. So let me give here highly unbalanced tree. So let's consider one example. So let me show this one. So when I say highly unbalanced, we are just considering skewed to one side, left side. Let me consider here. Let me consider one more node here. This is fine. So here you can clearly see the height is here in this case 1, 2, 3, 4 height, and we don't have right at all. So here this one would be 4 minus 0. So output will be false here in this case. So output will be false here. So these are the edge cases that we need to this one keep in mind. One is for the empty tree with only one node. Third one was for this one, perfectly balanced tree. This is for perfectly balanced tree. And the final one is for the this one, highly unbalanced tree. It is only skewed to one side. So this will lead to the output false as well. So this is these are the edge cases that we need to consider. Now let's start writing the code. I'll just explain the code while we write the code. And then let's discuss the complexities of the code that we have written. Let's start writing the code here. The first thing we have to do is we have to track if the tree is balanced or not. So I'll just consider initially it will be balanced. So I'll just give here let balanced equals true. After this step, what we'll do, let's consider the helper function. In this case, we have to find the depth of the left and right subtree, right? So I'll just go with recursive function depth in this case. Let's pass the parameter node here. So within this, let's consider the base case, nothing but if the node is null, we have to return height as 0. So this will be if not of node, then let's return this one as 0. This is fine. Then the next step is we have to recursively get the left subtree height and we have to recursively get the right subtree. So this is simple. So I'll just give here for the left subtree, I'll just consider L. This will be depth. So we are going with the recursive function, right? Let's consider depth here. Node dot left. Same thing goes with right as well. So I'll just copy, paste this one and make the necessary changes. This will be R. This will be, we are considering for the right? So this is fine. So the next step is, if the difference is greater than 1, then we have to mark that one as not balanced. So absolute difference we are considering, right? So I'll just consider here math.abs, nothing but absolute. So this will be L minus R. We have seen this one in the example. I have shown this one by taking the example, first example and second example that they have shown this one question itself. So if the difference is greater than 1, we have to mark that one as not balanced here, right? So L minus R, if it is greater than 1, balanced here, this will be, we are setting the balance to false. So the final step is we have to return the height of the current node. So how can we return the height of the current node? So I'll just give here math.max of left and right plus 1 because the binary indexing of the binary tree starts from 0. I hope this is clear. Finally, we have to start we are starting the recursion from root. We have to start the recursion from root. So yeah, let's go with the recursive function depth. and let's start the recursion from root. I just pass the root here. So final step is we have to return the final result, nothing but balanced in our case. So I'll just give here balanced. So let me format the code once and let me hit the run button. So now you can clearly see here the sample test cases are getting passed. So the code works absolutely correct here. Let me hit the submit now. Let's see whether all the test cases get passed or not. So here you can see all the test cases are getting passed. So the code works absolutely correct here. Let's quickly discuss the time complexity and the space complexity of the code that we have written. So here the approach that we went with here is DFS with post order traversal. We have already discussed this one. So what will be the time complexity here? The overall time complexity would be big O of n. Why the overall time complexity here would be big O of n? Because we are visiting the each node once. We are making use of the recursion, right? So recursive stack. So we are visiting the each node once, and so the time complexity would be big O of n. And what will be the space complexity here? Overall space complexity here would be big O of h. Why the overall space complexity here would be big O of h? Because we are making use of the recursive stack space. We know that one. H is nothing but height of the h here, whatever I have given. H is nothing but the height of the tree. We know. In worst case, for the skew tree, the space complexity would be big O of n, and for the and when we consider the best case, it would be big O of log n for the balanced tree. So overall space complexity we can just consider here as big O of h, where h is nothing but the height of the tree. So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.